Hello, I'm Adam, and I work at Oracle, MySQL, developing Boost geometry. Well, I cannot start now, but this is basically my introduction. So, yeah, so we are developing at Boost Geometry. We are developing algorithms and data structures, which are then used by MySQL to provide well, geometrical computation when you're calling SQL MM or SQL SFA features like ST intersection or something like that. Then internally, MySQL calls Boost geometry functions.
That was a quick talk.
Only the simple ones like boxes and points. Polygons are 2D. The library allows it. I mean, the interface allows it to be expanded this way, but we're not there yet.
A real roadblock for our open source community to do indoor mapping.
Right.
Keep looking for anyone with deep funding skill.
Okay, you're ready to go.
Okay, so again, hello, I'm Adam. Welcome to the talk about Boost Geometry R3. For those of you who don't know, Boost Geometry is a C++ library, part of Boost C++ libraries, and we provide primitives, algorithms, and spatial index for you to use in your C++ code. And the library is used by MySQL for GIS features. The R3 is a self-balanced tree, which is used for spatial searching and KNN searching. And there are various balancing algorithms or various ways how the R3 can be created. When you are putting elements one by one, then tree is balancing itself. And there are also a class of algorithms which are used to create the R3 from a number of elements at once. And this is called packing or bulk insertion algorithms. And the specific features of Boost geometry implementations are listed on the slide. So the class is in Boost geometry index namespace. It allows you to store your own user-defined types. By default, it supports any type adapted to point, box, or segment concept from Boost geometry library, and also supports pairs and tuples. There are 3 balancing algorithms. I'll show them later. The nodes, the size of a node is defined by the numbers of objects stored in a node, as opposed to, let's say, database implementations of the R3 where the size of a node is defined by the page size. And it allows you to perform advanced queries. I also show them later what that means, and iterative queries. So here are the examples of internal structures of R3s created in different ways. Linear, quadratic, and R tree versions are the ones created using balancing algorithm, and packing is the packing algorithm we use. It's a version of STR algorithm, so sort tile recursive variation. And as you can see, the internal structures are different. Some of them will be better for searching because in some of them there is more overlap of the nodes. Some of them have big nodes, some of them have smaller nodes. So the less overlap, the less number of nodes, and the smaller nodes are better for searching later. But yeah, how you can expect, it takes more time to create a better structure of the R tree. So these are the times. In general, the more time you spend on creation, less time you will spend on searching, right? So there's a trade-off. And depending on your application, you have to choose one or the other. And packing is, the tree created with packing algorithm is the best in all situations, but on the other hand, you have to know all of the elements in front of the creation. And there's also one more decision you have to make before creating the R tree, which is the size of the node. The size of the nodes, the number of elements stored in the node, which will be influenced by your knowledge about the domain you're working with, and specifically about the kind of data you're working with. So for non-overlapping elements, the tree will behave differently. Like here are times of creation. For number of elements stored in a node. So here is nothing interesting actually. Just maybe just that the creation of the tree is longer for all algorithms when there is overlap. But if you see the searching, then here we have something interesting. It seems that for overlapping nodes, for overlapping elements, if you have too small number of elements stored in a node, then you increase the time of search. So the more overlap you have in your data, the bigger the node should be, basically. Later we can talk about it after the talk, why that is. And by overlapping, I mean like physically overlapping in 2D, like for instance, if you have big objects overlapping each other, or you have objects in higher dimensions, then there is more probability that they will overlap. Okay, so now a few examples. I'm using the data from this website. So here are the includes and some namespaces I'll be using in the code. The second one is only if you clone the repository from GitHub, because it's a part of the code which we call extensions, but it's only for loading a shapefile. Yes, and these are basic definitions of types I'll be using. In Boost Geometry, the default way of defining the coordinate systems that are used in data are part of a point type. So here's how you can create a type capable of storing Cartesian points, spherical points, and geographic points. I'll be using the last one in the examples. There are other ways how we can affect the algorithms, and also like use different spheroids and things like that. But for the time being, let's assume that when I'm using geographic points, it's WGS 84, and I'm calculating stuff on the surface of ellipsoid. So we are not doing any projections. We are on the surface of ellipsoid, which is good for a class of problems that are global, where you cannot choose the best projection, and you just want to stay. You could approximate the globe with a sphere, but here I'm showing the geographic. How to deal with geographic data. Yeah, so for this you'll need the for loading the data I'm showing, you'll need the extensions, but you can do it however you like. You can write your own shapefile importer or fill the data whatever you like. And the first example will be to find points which are near another set of points, basically. So this is the data from this website. One is populated places, which are defined like a point representing a place where at least 1,000 people live or something like that, and the green dots are airports. So I'm searching whether or not some airports are near the populated places like that. And by small area, I mean a box. So here is, let's say, naive example, which has quadratic complexity. And what I'm doing is I'm iterating over all the places, then over all of the airports, and I'm checking if an airport is covered by a box, this small box I created. And then I'm printing a result. So I'll show the timings later for the other algorithm, but as you may expect, quadratic complexity we can do better. So for this purpose, we create R3, storing points, and this will be R star variant, storing 4 elements per node, and I'm calling insert for all of the airports, which forces the R3 to use balancing algorithm instead of packing, because I'm inserting one by one. And then I'm iterating over all the places and performing a query, passing covered by predicate to the query function of the R3, and taking the result as an output iterator, which in this case is back insert iterator. But we can do better because we know the data up front. So I'm creating the same R3 but using packing algorithm, and for this purpose I'm passing the iterators to the range into the constructor of the R3. So here we have all of the R3 created with packing algorithm, which should be faster. And then I'm using query iterators instead of query function, which iterates over, lazily iterates over the results. So you can, for instance, stop it at some point if you like. And if you, sorry, if you prefer working with ranges instead of iterators, then the R3 also supports it. So I'm just passing a range of elements, which are then stored in the R3 using packing algorithm. And then instead of standard for each, I'm using range-based for loop. And for that, I'm creating a range, a queried range, using a range adapter, similar to boost range adapters. So what's the red now is a range representing a pair of iterators, basically, just as it was on the previous slide. And here's my result, so some pairs of points which are close to each other. So the next example, which will be more interesting maybe. So now I'm a traveling salesman and I want to go through all of the airports on the world as fast as possible, right? So classic problem. Again, so this is my initial preparation where I have airports. I'll be storing the result in a line string containing geographic points, and I also need a structure, helper structure for to store flags whether or not I visited an airport or not. Here is one of the possible solutions which is the classic one, which is called greedy heuristic. So basically, I'm choosing the closest airport from a starting point, and then from that, I'm choosing the closest airport again and again, 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 and again. And I'm doing it until I have all of the airports. So yeah, until I have all of the airports, I'm traversing all of the, checking all of the airports, checking the ones which are not visited, calculating the distances, picking the smallest one, and then when I have the smallest one, then I'm adding it to the solution. But again, the previous algorithm has quadratic complexity, so we can do better. And here I'm using the R tree for that. I'm storing a pair of my point and an index. I need an index to in order to access the flags, visited flags. So I'm storing a pair. This works by default. And I could create a vector of pairs first, but I decide to do it on the fly using boost range adapters. So here I'm creating a range representing, first transforming or indexing airports with an index starting from 0, and then transforming this range of indexed airports into range of pairs. This is what you can do with boost range adapters. So I have all of the data needed in my R tree, and then I'm doing again the same until I have all of the points. I'm performing query, but this time I'm not traversing all of the airports to search for the closest point, but using the R tree for that, and I'm passing the nearest predicate, and I need the nearest point. Nearest point, which also satisfies this condition that it is not visited, right? And then I have one in the result. I'm passing, as output iterator, I'm simply passing the pointer. And I'm putting the result in the root line string and setting a flag. And that's it. And this is my result. So a traveling salesman went through all of the airports, at some point traversing the anti-meridian, so the daytime change line. Yeah, so this looks good, and the whole route is like 400,000 kilometers long. And this is some benchmark of both algorithms. The one with quadratic complexity is gray. And as you can see, the solution using R tree is behaving better, right? And that's it from me. Thank you. And there are 3 minutes.
Thank you. We have some time left.
Yeah.
Let's say about 3 minutes for questions. Any questions that you want to sort of throw at him? Hi. Are there any questions for you that you want to sort of ask the crowd? What do you want
Me?
from them? How can they help you?
Probably to check out the boost geometry, try to do something interesting with it. Like if you have a problem to solve, just consider trying boost geometry and then maybe share a feedback or something like that. And there's one question or two questions.
Could you speak up a little bit, please?
Okay. I just confused about you said that the implementation has default support for 90 milliseconds.
So we're talking about this one, okay?
My understanding for R3 everything is a box.
Okay.
So are you doing something different or?
Yes. So the objects representing the internal nodes of the tree are, in fact, as you said, boxes or rectangles. However, in leaf nodes, so at the lowest level, I can store various things, and I've chosen to allow to store simple geometries like points, boxes, or segments. So, because otherwise you'll be forced to, for instance, represent a point as a box, right? And then you have a duplication of data, basically. So this is why it is possible in Boost to just store points. And the R tree is parameterized, like it allows you to pass data type or value type in compile time as a template
This doesn't affect
argument.
the traversal that way the searching with the tree.
Sorry?
This doesn't affect the traversal, the searching with the tree.
No. It's only a matter of storing data in leaf nodes. We can talk about it more after, because unfortunately.